Good morning, all of you. Today, we are going to see close packed structures. We'll be seeing the close packing of atoms. Now, you see, these atoms are arranged in a line. Coordination number of an atom, we have to consider an interior atom. So, coordination number of an atom means the atoms which are present in the immediate contact. The number of atoms that touching a particular atom. If you are considering this one, it is touching two atoms. You have to consider an interior one. So this is close packing in one dimension. The number of nearest neighbors in contact, that is called coordination number. The number of nearest neighbors in contact, that is called the coordination number. So coordination number in one dimension is here 2. This is one dimension close packing. Atoms are touching. Now I am going to close packing in 2 dimension. There are 2 ways of arranging these atoms in 2 dimension. Let's see. You see this arrangement? Here, this is the first row, this is the second row, and this is the third row. This is one dimension. The coordination number in one dimension we have seen 2. But when you make a 2D structure, see, second line balls or spheres or atoms are arranged in alignment with the first line, first row. And third line balls are just below the second line. So in this case, what is the coordination number of an interior atom? You can select this one. This is in contact with 1, 2, 3, 4. So the coordination number of this interior atom is 4. This is close packing in 2 dimension, 2D. But this is an inefficient packing. You can see lot of space wasted over here. Lot of space is wasted. So this is an inefficient packing. This is 2D packing, which is inefficient. This is one way of packing. Another way of packing, which is more efficient than this packing, is what? You can keep this ball in the depression made by these two. If I keep this ball here, then lot of space is utilized. It is an efficient packing. So that is second type of packing, which is more efficient. I'll show that also. Look at this packing. This is the first row, and the second row balls or spheres or atoms are kept in the depression of the first row. This is the depression, this is the depression, this is the depression, depression, like that. And the third row balls or atoms or spheres are kept in the depressions of the second row. This you can make out from here. This is a more efficient packing. This is again 2-dimensional packing. The coordination number of an interior atom, suppose you are taking this one, it is in direct contact, in touching with how many balls, how many spheres, how many atoms, how many particles? 1, 2, 3, 4, 5, 6. So in this packing, this is hexagonal close packing in 2 dimension. What is hexagonal close packing? Hexagonal close packing means you see a hexagon. If you join the centers of these spheres, this is 1, 2, 3, 4, 5, 6. If you join the centers of these spheres, touching spheres, you'll be getting a hexagon. So this is called HCP, that is hexagonal close packing. This is a more efficient close packing. Now we are going to place the second layer. In the first case, if you place the second layer, you can keep, suppose an inefficient packing if you are thinking of, you can keep the balls, spheres or atoms or particles of the second layer just above these green balls, like this. So here, two here, and two down. So in that case, that is again going for an inefficient packing. In that case, you will be getting a square close packing. We call it as square close packing. This is square close packing in 2D and square close packing in 3D. In that case, you will be getting like this. The unit cell will be like this. That accounts for primitive. What we have learned already, primitive means atoms are only at the corners of this cube. So if I take out these four spheres and the spheres just above this, four spheres just above this, like this, four spheres just above this, what I am going to get is a square close packing in 3D, which is called primitive. Its unit cell is primitive. This is again an inefficient packing. Let's go to the second type, efficient packing for 3D. In this packing, you see the gaps here, a triangular shaped gap. For that gap, in chemistry, we call void, V-O-I-D. This is a triangular void, a triangular void, a triangular void, triangular void. So, only one type of voids are there, triangular voids. Triangular void pointing downwards, triangular void pointing upwards, triangular void pointing downwards, triangular void pointing upwards, downwards, upwards, downwards. Anyway, all the voids are triangular voids only. I'm going for a more efficient packing. If I keep the balls or spheres or atoms or particles of the second layer, how? On the triangular voids, means here. Like this. So when I keep on this triangular void pointing downwards, then I will not be able to keep a ball here. Then I can keep on this triangular void. Here one ball will be there, here one ball will be there. At that time, I will not be able to keep on this. So if you are keeping on triangular voids pointing downwards, then you will not be able to keep the balls on the triangular void pointing upwards. Anyway, only one type of voids are there, triangular voids. When I keep the ball of the second layer on the triangular voids, see, here I am keeping, then I can keep here only. Then that means on this gap, we will not be able to keep. So there is only one way of keeping the balls of the second layer. That is either triangular void pointing upwards or triangular void pointing downwards. So when I keep this second layer ball, then I'll be getting a different alignment compared to this first layer. This first layer is called A layer. This alignment, this arrangement is called A layer. When I keep the bolts of the second layer like this, like this, like this, these bolts are not in alignment with the A layer. It's a different alignment. So that different alignment and that layer, what we are getting is called B layer. To show that different alignment, I'll show the second layer alignment also, like this. If you consider iron crystal, iron solid, then all atoms are iron only, IRON. But here, just to show the difference of the alignment of the second layer, I change the color. Otherwise, I would have kept only that orange color. So this orange layer balls are A layer. So the yellow color balls are of B layer because their alignment is different from A layer. See, I have kept a yellow ball here. Then I am not able to keep in this triangular void. I could keep here. So in this I am not able to keep. I kept here. In this I am not able to keep. I kept here. In this I am not able to keep. So only one option. Either triangular void pointing downwards or triangular void pointing upwards. Be careful that only one type of voids are there, that is triangular voids. So, second layer balls or second layer spheres or second layer atoms or second layer particles are having a different alignment. So, we call that second layer as B layer. So, first one A layer and the second one B layer. This is a hexagonal close packing in 3D. Previously, what we saw, this is hexagonal close packing in 2D. The coordination number here is 6 because it is 2D. For finding out the coordination number, you have to consider an interior ball because crystal lattice is made up of arranging these atoms in different directions one over the other to get the 3D. So this is a 2D. So here the coordination number is 6. Now we are going for 3D. Second layer is kept. Again we are going for the next layer. That means placing the third layer. Before placing the third layer, you look at the voids made by these two layers together. You see, here there is a gap. This void is called not a triangular void because that void is made up of four balls, three yellow ball and one orange ball. So three yellow and one orange. So this void is not called a triangular void, what we have seen when we place the first layer, A layer. This is called a tetrahedral void, not a triangular void because this is made up of two layers. This is a tetrahedral void. Why are we calling it as a tetrahedral void? Because this void can be occupied by a small cation. I can keep a small ball inside that. This can be considered as a cation. When I keep the small ball inside, the small ball will be in contact with how many big spheres? Four big spheres. When you join the centers of these four big spheres, that means three yellow and one red. When you join the centers, its center, interior center, its interior center, and that this red one, what you are seeing through this gap, you will be getting a regular tetrahedron. So we call this void or that cations, that void or gap, and a tetrahedral void. That void is called a tetrahedral void. So I'm going to take out these three balls and that behind one, that red ball. Let's see what's the situation. Three yellow balls means two down and one up. Okay, here. This one, this one, this one. One down and two up. One down and two up. One is behind. What you are seeing through this gap. So I'm keeping two balls and one down and behind this an orange one. So like this. This is the situation. Two yellow balls up and one down. Behind is one orange one. So I am taking it like this. The same thing, I have just taken out and I'm showing you in a proper way. So this was that behind one, back ball, and this was the situation, two up and one behind. So I'm keeping it like this. You see. When you join the centers of these four spheres, you are getting a tetrahedron. You are getting a tetrahedron. So, you can see that small ball here, one small ball here. In that void means a small cation can be kept. That void can be, the tetrahedral void can be occupied by a small cation. That small cation is in contact with these four balls, these four spheres, these four atoms, these four particles. This tetrahedral void, it is a smaller void, a smaller gap, a smaller cation can be kept inside. This tetrahedral void can be occupied by a small cation. So this is one type of void what you are seeing by placing the second layer. So what void we have considered? These two, means these two balls, one ball. So three yellow balls and one orange ball. So this void in which a small cation can be kept, the cation will be in contact with these four balls. We say the coordination number of that small ball, small cation, the coordination number of the small cation is what? 4. Because it will be in contact with four balls. So this is one type of void that you are visualizing. Now, one more type of void is there. See this void. You can see I have given a white background that, so this void, that void, can you see this white color? I have given a white background so that you can visualize that void. That void is made up of 6 balls, 6 spheres, 6 atoms. I'm talking about this void. First, we saw this tetrahedral void. Now we are going to see another type of void that is called octahedral void, which is made up of 6 spheres, 1, 2, 3, and behind 3, see this void. Behind there are 3 orange balls. So 3 yellow balls and 3 orange balls behind. So altogether 6 balls are there, 6 spheres are there. So these 6 spheres together make this type of void, which is called octahedral void. This void we call tetrahedral void, which is made up of 4 spheres. But this void that is made up of 6 balls, 1, 2, 3 in front and 1, 2, 3 behind. So altogether 6 balls, this gap. Now this is again a tetrahedral void made up of 4 balls, and this is an octahedral void. This is an octahedral void. Then tetrahedral void, octahedral void, tetrahedral void, octahedral void. Octahedral void. So, 2 types of voids are there. When you made this, only one type of voids were there. That is triangular voids. Now, when you made the second layer also, now 2 types of voids are there in 3D. So here, this is tetrahedral void, octahedral void, tetrahedral void, octahedral void, tetrahedral void, octahedral void. And here, if I keep one ball over here, then this is a tetrahedral, tetrahedral, tetrahedral. Here it is octahedral, octahedral. So 2 types of voids are there. Now we are going to place the third layer. So 2 types of void what we are seeing. You see, this is tetrahedral void, octahedral void. Now we are going to this details of octahedral voids. I told you this is a gap. In this gap also we can keep a cation. This octahedral void is bigger than, actually this is bigger than this tetrahedral void. So a bigger cation can be kept inside. This octahedral void can be occupied by a bigger cation. Now what is the coordination number of that bigger cation? 6, because that bigger cation will be in contact with 6 balls, 6 spheres, 6 particles, 6 atoms. What are these 6 atoms? These three yellow and those 3 orange behind. I'm going to take out these 6 balls, 3 yellow and 3 orange. So these 3 yellow means 2 down and 1 up. See, 2 down and 1 up. So behind, orange balls will be 2 up and 1 down. So I am going to keep those also. 2 up and 1 down, like this. This is the situation. Yellow, 2 down, 1 up, and orange, 2 up, 1 down. I'm going to take out these 6 balls from that arrangement. I'm taking out, I cut those 6 balls, and I'm showing you the same thing. I'm just tilting and showing you like this. Now you see, it was like this, the same thing. I'm keeping it like this, or I'm keeping it like this. So here, you can see 1 ball up and 1 down. One yellow ball up, 1 orange ball down. And 4 balls, 2 yellow and 2 orange. They are at the corners of a square. They are at the corners of a square. So these square corners, that means these 2 yellow and 2 orange. Previously it was like this. The same thing. That is 2 yellow down and 1 yellow up. 2 orange up and 1 orange down. Now the same thing. Once again, 2 yellow down and 1 orange up. Second layer. And 2 orange up and 1 orange down. This is the situation. The same thing I am taking out from this arrangement. I'm just tilting. I'm just tilting so that 1 is up, 1 is down. Or I can show like this also. 1 is up, 1 is down. Now, 1 yellow, its center, and down. You take the center of this down orange ball. From that, you join that top center to the corners of the square what we have imagined. If I take out that 1 down ball, the situation will be like this. If I take out this yellow ball, the situation will be like this. See, this previously it was there. I removed that. 1 behind also. 1 yellow behind also, I removed. So now, what I am saying, if I join the centers of these 4 spheres, I'll be getting a square. And on to that corners, from its center, you join to the corners of that square. Similarly, from that From the center of this behind orange ball, you join to the corners of that sphere, square. What shape you are going to get? What you are going to get is an octahedron. What you are going to get is an octahedron. So we are calling it as an octahedral void. So this is an octahedral void. First, once again, I'm showing. These two down, one up. Two down, two down, one up. Two up, one down. This is a situation. I just showing you like this. Join from the top yellow to the corners of the square. Similarly, join from the center of the bottom orange. Join to the corners of the square. You will be getting an octahedron. So we name this void as an octahedral void. A cation can be kept inside this void. So we have seen two types of voids, octahedral voids and tetrahedral voids. Tetrahedral voids and octahedral voids. Tetrahedral voids are obtained by four spheres. So, void's coordination number is 4. But octahedral voids are obtained by six balls. Coordination number 6. Tetrahedral voids are smaller. Octahedral voids are bigger. Now, I told you you can keep a small cation inside this. You can keep another cation here. If you consider the radius of that smaller cation as r and the radius of this bigger atom as capital R, then R is equal to, in the case of tetrahedral void, it is 0.225 capital R. That means radius ratio. Radius ratio, small r by capital R is equal to 0.225. In the case of octahedral void, small r upon capital R is equal to 0.414. So this we will be deriving these two radius ratio. So these are the differences between tetrahedral voids and octahedral voids. Octahedral void is bigger than tetrahedral voids. You can keep a bigger cation there. In tetrahedral voids, you can keep a smaller cation. So these are the differences between tetrahedral voids and octahedral voids. Now, in the next class, you will be placing the third layer spheres, third layer atoms, third layer balls on either all these octahedral voids or on all the tetrahedral voids. Anyway, octahedral voids and tetrahedral voids may or may not be filled at the same time because the cation size is smaller, means they are different. So, one case is either all tetrahedral voids can be filled or all octahedral voids can be filled. Tetrahedral voids, all tetrahedral voids may or may not be filled. All octahedral voids may or may not be filled. Some of the tetrahedral voids and some of the octahedral voids may be filled. So all possibilities are there. So I am stopping here. Tomorrow we'll be placing the third layer. Thank you.